Just as in single variable calculus you saw applications of integrals, now we're going to look at applications of double integrals. When you looked with single integrals, you may have seen that you can find the mass of a lamina, which is a thin plate that has a constant density rho. Now we're going to consider a lamina that's in the shape of a region D in the xy plane that has variable density rho of xy. This looks like a P, but it's the Greek letter rho. And to develop the mass of such a plate, we're going to approximate the mass by considering a bunch of small rectangles with area delta A and containing x sub ij star, y sub ij star, which is an element in the ijth rectangle. We're going to sum together a bunch of little masses, and we're going to get that the mass is approximately the sum as I goes from 1 to m of the sum as j goes from 1 to n of rho of x sub ij star, y sub ij star, delta A. Taking limits as m and n go to infinity is going to yield that the mass is equal to the double integral over the region D of rho of xy dA. Now folks, this double integral is not any different than a double integral that you saw in a previous section. Here though, instead of f of xy, we have rho of xy, implying that the function that we're integrating is a density function. You see, if this is f of xy, then we end up with a volume. But in this context, since rho is a density, we're going to end up with a mass. And as in single variable calculus, mass can be used to find, for instance, a center of mass. We'll see how in just a little bit, but first I want to give you another application for this same type of integral here. If sigma represents a charge density, then we can find the total charge over an area. The symbol we use for charge is Q, and the total charge is going to be the double integral over D of sigma xy dA. I'll point out here that this is a sigma, lowercase Greek letter, excuse me. And folks, what you can see here is that this integral is exactly the same form as the one we just wrote down and the ones that we were working with in an earlier section. As with so many things, the meaning depends on context. I mentioned something a moment ago about centers of mass. Before we get to that, we need to talk about moments. We're going to look at moments about the x and y axis, and a moment is a tendency of a shape to rotate. If you pick up just about any object around you, a phone, a tablet, a book, whatever, try to balance it on your finger. If it tries to flip, that thing that makes it want to flip is what's called a moment. The moment about the y-axis is the tendency to want to flip in the x direction, and it is given by m sub y is equal to the double integral over d of x times rho of xy dA. What you essentially have is the rho of xy dA is going to give us our mass, and then x is the distance from the y-axis. So mass times distance gives us that moment. Similarly, the moment about the x-axis is m sub x is equal to the double integral over the region D of the distance from the x-axis, which is y, times rho of xy dA. The center of mass is x bar y bar, where x bar is equal to m sub y over m, the total mass, and y bar is equal to m sub x divided by m, the total mass. Physical systems also have what are known as moments of inertia. They are also called second moments, and we consider moments about the x-axis, the y-axis, and the origin. Moments of inertia are the rotational equivalent of mass for linear motion. As you probably know, mass is what makes an object either hard to start moving or hard to stop moving. And a moment of inertia is what would make an object either easy to start and stop spinning or hard to start and stop spinning. Think about a spinning bicycle tire and trying to stop it, and a spinning semi-wheel and trying to stop it. the semi-wheel has a larger moment of inertia. About the x-axis, we have that I sub x, that's how we refer to the moment of inertia, is the double integral over d of y squared times rho of xy dA. About the y-axis, it's I sub y is equal to the double integral over d of x squared times rho of xy dA. But here we also have a third one about the origin. This one's denoted I sub o, and it is equal to the double integral over d of x squared plus y squared times rho of xy dA, which means it's equal to I sub x plus I sub y. And finally, we have something called radii of gyration. I do not make this up, folks. The radius of gyration with respect to the x-axis is given by y double bar squared is equal to I sub x, the moment of inertia about the x-axis, divided by m, the total mass. And the radius of gyration with respect to the y-axis is x double bar squared is equal to I sub y divided by m. And so what you would do is you would find the integral I sub x, you would find the integral m, find their ratio, and then square root them. X double bar y double bar is the rotational equivalent to the center of mass. If all the mass were concentrated here, then the moments of inertia would remain unchanged. It's kind of the center of the tendency to rotate.